beneath the complexities of everyday life, the rules of our universe seem reassuringly simple. This solid bridge supports my weight. The water flowing underneath always goes downhill. And when I throw this stone, it always flies through the air following a predictable path. But as scientists peered deep into the tiny building blocks of matter, all such certainty vanished. They found the weird world of quantum mechanics. Deep down inside everything we see around us, we found a universe completely unlike our own. To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. Around 100 years ago, some of the world's greatest scientists began a journey down the rabbit hole into the strange and the bizarre. They found that in the realm of the very small, things could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. And at stake, that everything we thought we knew about the world might turn out to be completely wrong. The story of our descent into scientific madness begins with a most unlikely object. Berlin, 1890. Germany is a new country, recently unified and hungry to industrialize. In this newly unified Germany, a number of new engineering companies were founded. They spent millions buying the European patent for Edison's new invention, the light bulb. The light bulb was the epitome of modern technology, a great optimistic symbol of progress. Engineering companies quickly realized there were fortunes to be made building streetlights for the new German Empire. But what they didn't realize was that they would also unleash a scientific revolution. Strangely enough, this humble object is responsible for the birth of the most important theory in the whole of science, quantum mechanics, a theory that I've spent my life studying. And that's because back in 1900, the light bulb presented a rather strange problem. Engineers knew that if you heated the filament with electricity, it glowed. The physics that underpinned this, though, was completely unknown. But something as basic as the relationship between the temperature of the filament and the color of light it produces was still a complete mystery. A mystery they were obviously keen to solve. And with the help of the new German state, they saw how to steal a march on their competitors. In 1887, the German government invested millions in a new technical research institute here in Berlin, the Physikalisch-Technische Reichsanstalt, or PTR. Then, in 1900, they enlisted a bright, if somewhat straight-laced scientist to help work here. His name was Max Planck. Planck took on a deceptively simple problem: why the color of the light changes as the filament gets hotter. To get a sense of the puzzle facing Planck, I'm going to ride this bicycle with an old-fashioned lamp powered by an old-fashioned dynamo. Obviously, the faster I go, the brighter the light. The more I pedal, the more electricity the dynamo produces, the hotter the filament in the lamp, and the brighter the light. But the light the bulb makes isn't just getting brighter. it's changing color too. As I speed up, the color shifts from red to orange to yellow.
Right, now I'm going to really belt it.
Now the bulb's filament is getting even hotter, but although it certainly gets brighter, the color seems to stay the same, yellow-white. Why doesn't the light get any bluer? To investigate, Planck and his colleagues built this, a black body radiator. It's a special tube they could heat to a very precise temperature and a way to measure the color or frequency of the light it produced. Nowadays, over 100 years later, the PTR still do exactly this kind of measurement, just much more accurately.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color.
It's about the same color as my bike light when I'm cycling slowly. But I want to see something hotter still.
The temperature inside here is about 2,000 degrees centigrade. And it's glowing with a much brighter, whiter colored light. To produce light of this intensity and color requires a power of about 40 kilowatts. Now, that's equivalent to about 400 Ms on a bike cycling very fast, or the combined output of the entire Tour de France.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue, the so-called ultraviolet is hardly produced at all, even when we look at things as hot as the sun.
Even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make? This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it the ultraviolet catastrophe.
Planck took a crucial first step to solving this. He found the precise mathematical link between the color of light, its frequency, and its energy. But he didn't understand the connection. However, it was another weird anomaly that would really put the cat amongst the pigeons.
In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disk, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse.
Light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. The ultraviolet catastrophe and the photoelectric effect were big problems for physicists, because neither could be understood using the best science of the time. The science that said quite unequivocally that light was a wave.
All around us, we see light behaving in a perfectly common-sense, wavy way. Look at the shadow of my hand. It's fuzzy around the edges.
We understand this as the light hitting the sides of my hand and bending and smearing out slightly, just like water waves around an obstruction.
Perfectly common-sense, wave-like behavior.
And here's something else, something rather beautiful. Look at these soap bubbles. Shine a light on them and gorgeous colored patterns emerge from nowhere. And this was easily explained if you accept that light was a wave, reflecting off the outer and inner layers of the thin soap film and breaking up into the colors of the rainbow. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly accepted as the fact that the Earth was round. But although this wave theory worked perfectly well for shadows and bubbles, when it came to the ultraviolet catastrophe and the photoelectric effect, the wheels started coming off.
The problem was this: how could light do this? To truly grasp how absurd this phenomenon was, it might be useful to consider how waves in water behave.
This is the wave tank at the RNLI's headquarters in Dorset. It's used to train lifeboat teams to deal with a range of different kinds of water waves. First, small waves, just 30 centimeters high.
These waves don't have much energy, hardly enough energy to knock this top can off the other.
But when the waves grow to over 1.5 meters, it's a very different proposition.
And they're really throwing me about. There's no way I can keep this can balanced on the top.
It's clear what water waves are telling us. Bigger, more intense waves have more power. They easily knock me and the cans around. So if light was a wave, more intensity should knock out more electrons. But that's not what happened. Remember, no matter how intense the red light was, it still didn't budge electrons from the metal. But weirdly, weak ultraviolet worked within seconds. So thinking of light as a wave just wasn't adding up.
To resolve this, someone needed to think the unthinkable. And in 1905, someone did. You may well have heard of him. His name was Albert Einstein.
This is the Achenhold-Sternwarte Observatory in Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually a telescope. Built in 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and astound the public in new science.
Albert Einstein gave a very famous public lecture here on his theory of relativity, which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize.
In 1905, he'd also come up with a new theory to explain the photoelectric effect. And what he suggested was revolutionary and even heretical.
He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles. The term he used to describe a particle of light was a quantum.
To Einstein, a quantum was a tiny lump of energy. And although in 1905 the word wasn't new, the idea that light could be a quantum seemed crazy. And yet, following Einstein's heretical line of thought to its logical conclusion, solved all the problems with light at a single stroke.
I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta.
And those cans over there are the electricity held in the metal.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
Absolutely no effect. That's just like red light. According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls.
Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these.
They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf.
So Einstein's idea that light is made up of tiny particles or quanta is a wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance and simplicity.
But what's more, Einstein's nifty idea also helped solve Planck's mystery of the light bulb. There was more red than ultraviolet because ultraviolet quanta took so much more energy to make, about 100 times more energy. No wonder there are so few of them.
That moment at the beginning of the 20th century signaled a genuine revolution because it demonstrated that the kind of physical science that people were doing right back to Newton and Laplace and people like that, that you needed a completely new approach. Physics has never recovered from that moment in the sense that it's built on that moment. That's where modern physics really began.
But Einstein's theory also left physicists with a dizzying paradox, defying all common sense. Light was definitely a wave, which explained shadows and bubbles. And now it was definitely a particle too, Einstein's quanta, explaining the photoelectric effect and the ultraviolet catastrophe.
Then, just a few years after Einstein's brilliant, crazy idea, the paradox got a lot deeper and a whole lot weirder.
because what seemed to be a curious mystery about light was about to become a battleground about the nature of reality itself. (1922). The Western world is in the grip of a revolution, a cultural revolution.
James Joyce's Ulysses is published. Stravinsky is at the height of his powers, and Chaplin has just released his first serious movie. The Ottoman Empire collapses. Europe is still recovering from the war to end all wars, in which millions of men lost their lives. Russia is newly communist. Meanwhile, America is exporting jazz to the world. Thank you.
In art, politics, literature, economics, there was an insatiable appetite for change. This was the birth of modernism.
You got a heart that there's no way of knowing. Can see where you are, but can't see where you're going. And I'm stuck here still. I'm tangled up with you. This whole world can be so uncertain.
But, and I might get into trouble for saying this, I would argue that the upheaval that took place in physics at this time would eclipse them all and have far longer-lasting consequences. It had begun with the discovery of the weird and contradictory wave-particle nature of light. It ended up as an epic battle fought between the greatest minds in science for the highest possible stakes, the nature of reality itself.
I know I deserve you, I know you're my savior, but when I observe you, you change your behavior. So
On one side, a new wave of modernist revolutionary scientists and their leader, the brilliant Danish physicist Niels Bohr. On the other side, the voice of reason, Albert Einstein, at the height of his powers and now world famous, a formidable adversary.
The battle raged for decades. Actually, in some ways, it still does. It was fought across the world in universities, at conferences, in bars and cafes. It would reduce grown men to tears. And it began with a deceptively simple experiment.
this whole world can be so uncertain.
But weirdly, it was an experiment that wasn't even about light. It was about the particles that make electricity.
Somebody else will
In the mid-1920s, an experiment was carried out at Bell Laboratories in New Jersey in America, which uncovered something entirely unexpected about electrons. Now, at the time, it was accepted without question that electrons were these tiny lumps of matter, small but solid particles like miniature billiard balls. In the experiment, they fired a beam of electrons at a crystal and watched how they scattered. Now, that's entirely equivalent to taking a beam of electrons, say, from an electron gun, and firing it at a screen with two slits in it, so that the electrons pass through the slits and hit another screen at the back.
What the Bell scientists found shocked the physics world to the core. To understand why, consider a similar experiment with water waves.
I've set up a simple experiment. I have a water ripple tank placed on top of an overhead projector. I have a generator producing waves that pass through two narrow gaps. The projector beams the image of the waves onto the back wall. You can see as the waves come in from the left and squeeze through the two gaps, they spread out on the other side and interfere with each other. What this means is that when you get the crest from one wave meeting the crest from another, they add up to make a higher wave. But when the crest from one meets a trough, they cancel out. This gives rise to these characteristic lines leading to the signature wave pattern.
bands of light and dark. Whenever you see these light and dark bands, the signature wave pattern, you know without doubt that you've got wave-like behavior. So, guess what they saw in New Jersey?
Now it seemed that firing electrons, tiny solid particles, through the two gaps produced exactly the same kind of pattern, bands of light and dark. First, light, for a long time believed to be a wave, was found to sometimes behave like particles. And now electrons, for a long time believed to be particles, were behaving like waves.
But it was actually stranger than that. The wave pattern wasn't merely some result of the entire beam of electrons.
More recently, this experiment has been repeated in labs around the world by firing one electron at a time through the slits onto the screen.
At first, each electron seems to land randomly on the screen. But gradually, a pattern forms. The signature wave pattern.
Let me be quite clear about just how weird this is. Remember from the wave tank experiment where the signature wave pattern only exists because each wave passes through both slits and then its two pieces interfere with each other. But here, every individual electron, each single particle, is passing alone through the slits before it hits the screen.
And yet, each single electron is still contributing to the signature wave pattern.
Each electron has to be behaving like a wave.
To explain this strange result, Niels Bohr and his colleagues created quantum mechanics, a crazy theory of light and matter that embraced contradiction and didn't care that it was almost impossible to understand.
As Niels Bohr himself said, anyone who isn't shocked by quantum theory hasn't understood it. So, viewers, I'm going to take our tiny electron and use it to delve deep into the heart of reality. And yes, prepare to be shocked, because this is the only way to explain what we observe when a single electron travels through the slits and hits the screen.
Quantum mechanics says this: we can't describe what's traveling as a physical object. All we can talk about are the chances of where the electron might be. This wave of chance somehow travels through both slits, producing interference just like the water wave. Then, when it hits the screen, what was just the ghostly possibility of an electron mysteriously becomes real.
Let me try and capture just how weird this is with an analogy. If I spin this coin, then all the time it's spinning, it's a blur. I can't tell if it's heads or tails. But if I stop it, I force it to decide, and it's heads. So before, it was sort of not heads or tails, but a mixture of both. But as soon as I've stopped it, I've forced it to make up its mind. This is what Bohr and his supporters claimed was happening with our electrons.
In a sense, as it spins, the coin is both heads and tails. Similarly, the electron's wave of chance passes through both slits, two paths at the same time. Our coin then stops at heads. The ethereal wave of probability hits the screen and only then becomes a particle. The quantum world was unlike anything ever seen before.
It's hard to overstate just how crazy this is. Bohr was effectively claiming that one can never know where the electron actually is at all until you measure it. And it's not just that you don't know where the electron is. It's weirdly as though the electron itself is everywhere at once. Bear in mind that electrons are among the commonest and most basic building blocks of reality. And yet, here's Bohr saying that only by looking do we actually conjure their position into existence. It's like there's a curtain between us and the quantum world, and behind it, there is no solid reality, just the potential for reality. Things only become real when we pull back the curtain and look. And this view, ladies and gentlemen, became known as the Copenhagen interpretation. Persuasive as it might seem, many people couldn't stomach Niels Bohr's outlandish ideas, and they found a natural leader in the most powerful man in science. Albert Einstein hated this interpretation with every fiber of his being. He famously said, "Does the moon cease to exist when I don't look at it?"
He was very unhappy because it gave limits to knowledge that he didn't think should be final. He thought there should be a better underlying theory.
Over the next 10 years, Einstein and Bohr would argue passionately about whether quantum mechanics meant giving up on reality or not. Then, with two other scientists, Nathan Rosen and Boris Podolsky, Einstein thought they'd found a way to win the argument. He was convinced he'd found a fatal flaw in the Copenhagen interpretation and its claim that reality was summoned into existence by the act of looking at it. At the heart of Einstein's argument was an aspect of quantum mechanics called entanglement. Now, entanglement is this special, incredibly close relationship between a pair of quantum particles whose fates are intertwined. For example, if they were created in the same event. Let me try and explain this by imagining the two particles are spinning coins. Imagine these coins are two electrons, created from the same event and then moved apart from each other. Quantum mechanics says that because they're created together, they're entangled. And now many of their properties are forever linked, wherever they are. Remember, the Copenhagen interpretation says that until you measure one of the coins, neither of them is heads or tails. In fact, heads and tails don't even exist. And here's where entanglement makes this weird situation even weirder. When we stop the first coin and it becomes heads, because the coins are linked through entanglement, the second coin will simultaneously become tails. And here's the crucial thing. I can't predict what the outcome of my measurement will be, only that they will always be opposite. Einstein seized on this because it meant that something was happening between the two coins that was almost too crazy to imagine. It's as if the two coins are secretly communicating instantaneously across space and time, even if the first coin was on Earth and the other was on Pluto. Einstein refused to believe this instantaneous, faster-than-light communication. His theory of relativity said that nothing could travel that fast, not even information. So how could one coin instantaneously know how the other would land? He disparagingly called it spooky action at a distance and claimed it was a fatal flaw in the Copenhagen interpretation. What's more, he had a better idea. Einstein believed there was a simpler interpretation, that somehow the destiny of the two coins, whether or not they ended up heads or tails, was already fixed long before we observed them. He said that although it seemed the coin was deciding to be, say, heads at the moment of observation, actually that decision was taken long before. It was just hidden from us. In Einstein's mind, quantum particles were nothing like spinning coins. They were more like, say, a pair of gloves, left and right, separated into boxes. We don't know which box contains which glove until we open one. But when we do, and find, say, a right-handed glove, then immediately we know that the other box contains the left-handed glove. But crucially, this requires no spooky action at a distance. Neither glove has been altered by the act of observation. Both of them were either left or right-handed glove from the beginning, and the only thing that has changed is our knowledge. So, which is the true description of reality? Bohr's coins, which only become real when we look at them, and then magically communicate to each other? Or Einstein's gloves, which are hidden from us, but are definitely left or right from the beginning? In other words, is there an objective reality, as Einstein believed, or not, as Bohr maintained? In the late 1930s, as the world plunged into war, there was no way to answer this question. The battle to understand the nature of reality was deadlocked. The war rolled across Europe, and many of the leading scientists fled to the United States. Then, as the Second World War led inexorably to the Cold War, American science, backed by dollar bills and a new vision of the future, boomed.
Remember, after the war, physicists came back raring to go and try to apply the ideas of quantum theory to atoms, the interaction between electrons and light and what have you. You didn't need to worry about the philosophical side of things to make progress with that. So, as you say, it really took a back seat.
Quantum mechanics led to a profound understanding of semiconductors, which helped create the modern electronic age. It produced lasers, revolutionizing communications, breathtaking new medical advances, and breakthroughs in nuclear power. Quantum mechanics was so successful that most working physicists deliberately chose to ignore Einstein's objections. It simply didn't matter to them because it worked. They even coined a phrase for it: shut up and calculate. And the price for this success was that Bohr and Einstein's debate on the reality of the quantum world was simply brushed under the carpet. And amidst all this success and pragmatism, there were few who still worried what it all meant. But as the 50s rolled headlong into the 60s, one lone dissenter worked out how to settle the argument once and for all. John Bell, I think it's fair to say, isn't well known to the general public. But to physicists like me, he's, well, a hero. He was an original thinker with real courage in his convictions, and the story of his rise to become one of the greats of physics is made even more remarkable when you consider how he started. He was born in Belfast in the 1920s into a poor working-class family. His father was a horse dealer, and they really struggled to get him into Queen's University, Belfast, to study physics. In fact, he was the only one in his family to even finish school. This, I believe, made him insatiably curious, fiery, and stubborn. I remember meeting John Bell in 1989, a year before he died. We were both at a conference in America, and we happened to be sharing a lift just after both attending a talk on quantum mechanics. Keen to say something to the great John Bell, I said I thought the speaker's conclusions were completely crazy. He stared at me with his piercing blue eyes, and for a moment I thought my fledgling physics career was going down the drain. But as the lift doors opened and he was about to leave, he said, "Yes, I completely agree with you. Haven't they heard of the helium problem?"
To this day, I'm not quite sure what the helium problem is, but I was just so relieved that John Bell and I agreed.
For many years, he worked here at Britain's Atomic Energy Research Centre at Harwell, who built this early experimental nuclear reactor called Dido.
It was here that he started pondering the deep and worrying questions that quantum mechanics raised. Did the quantum world only exist when it was observed? Or was there a deeper truth out there waiting to be discovered? In fact, he was so troubled, he began to wonder if there was a problem at the heart of quantum mechanics.
He famously said, "I hesitate to think it might be wrong, but I know it is rotten." And so in the early 1960s, Bell decided to try and resolve the crisis at the heart of quantum physics. It was an epic challenge.
After all, how do you check if something is real, if something is or isn't there, all without looking? How do you look behind the curtain without pulling it open? But John Bell came up with a brilliant way of doing exactly that.
I think this is one of the most ingenious ideas in the whole of physics. It's certainly one of the most difficult to understand and explain, but I'm going to try and have a go, and yes, I'm afraid I'm going to use another analogy. This time, I'm going to play a game of cards, but it's one for the highest possible stakes, the nature of reality itself.
The card game is against a mysterious quantum dealer. The cards he deals represent any subatomic particles, or even quanta of light, photons. And the game we'll play will ultimately tell us whether Einstein or Bohr was right.
Now, the rules of the game are deceptively simple. The dealer is going to deal 2 cards face down. If they're the same color, I win. If they're different colors, I lose. So, I have a red, so I need another red to win. That's black. I lose. Again, opposite colors. I've lost both those. That's 4 in a row. That's 6 pairs in a row that I've lost. Okay, I think I know what the dealer's doing here. Clearly, the deck has been rigged in advance so that every pair come out as opposite colors.
But there's a simple way to catch the dealer out.
So what we can do now is change the rules of the game. This time, if they are the opposite color, I win.
But once again, every time, my evil quantum opponent beats me.
But again, I can see what the crafty dealer could have done. Maybe while I wasn't looking, he's switched the pack and rigged it so that it always lands in his favor. Now every pair is the same color.
Rigged decks, remember, were what Einstein thought was really happening in the entanglement experiment. He said that just like the gloves were already placed in the box, so the evil dealer stacked the cards before we played. But Niels Bohr's idea was very different. He said red and black don't even exist until you turn them over.
Bell's genius was that he came up with a way of deciding once and for all who was right, Einstein or Bohr. This is how he did it. I'm now not going to tell the dealer which game I want to play, same color wins or different color wins, until after he's dealt the cards. Now, because he can never predict which rules I'm going to play by, he can never stack the deck correctly. Now, he can't win. Or can he? So now the rules are different wins. The same, okay? Same color wins. This gets to the very heart of Bell's idea. If we now start playing and I win as many as I lose, then Einstein was right. The dealer is just a trickster with a gift for sleight of hand. Reality may be tricky, but it does have an objective existence. But what if I lose? Well, then I'm forced to admit that there is no sensible explanation. Each card must be sending secret signals to the other across space and time in defiance of everything we know. I'm forced to accept that at the fundamental quantum level, reality is truly unknowable. Bell reduced this idea into a single mathematical equation that tells us once and for all what seemed unanswerable: how reality really is. John Bell published his idea in 1964, and the extraordinary thing is, at the time, the entire physics community ignored him. Total radio silence. It seems the world simply wasn't ready. Perhaps it was because his equation seemed untestable, or just because nobody thought it was worth investigating. But that was about to change. And the change would come from a very unexpected place. America was in crisis over Vietnam, Watergate, feminism, the Black Panthers. And while all this was going on, a small group of hippie physicists were working at the University of Berkeley in California. They did all the hippie things. They smoked dope, they popped LSD, they debated things like Buddhism and telepathy. And they loved quantum mechanics. In its weird version of reality, they saw parallels with their own esoteric beliefs. Their hippie New Age style physics also caught the attention of the public, who read their crazy hippie books that mixed quantum mechanics with Eastern mysticism. Books like The Tao of Physics, The Dancing Wooly Masters, and my personal favorite, Space, Time and Beyond, Towards an Explanation of the Unexplainable. But more importantly for our story, the story of quantum mechanics, these hippie physicists also turned their attention to Einstein's now famous thought experiment and what it told us about the nature of reality. They saw Niels Bohr's secret signaling as proof that physics supported their own ideas. Because if two particles could spookily communicate across space, then ESP, telepathy, and clairvoyance were probably true as well. If only they could prove it really existed. Then, in 1972, they realized that with a bit of mathematical sleight of hand, they could take Bell's equation and experimentally test it. One of their group, John Clauser, borrowed some equipment from the lab he was working in and set up the first genuine and ultimate test of quantum mechanics. This is a picture of that first experiment, built of leftovers and stolen equipment. Over the next few years, it was improved by a team led by Alan Aspect in Paris, making its results more reliable. Over 10 years after Bell first proposed his equation,
finally it could be put to the test.
This is a modern version of the experiment first carried out by John Clauser and then Alan Aspect.
Here, a crystal converts laser light into pairs of entangled light quanta, photons, making two very precise beams.
These photons are passed round and bent back again until they pass through these detectors.
The two photons are like the two cards the evil dealer places in front of me. We'll measure a property of the photons called polarization,
which is equivalent to the color of the playing cards in my game.
So, for instance, winning with two matching red cards might be the same as two photons with matching polarization.
But because this is quantum mechanics, it's more complicated than my simple card game.
And these dials here allow me to measure a second property of the photons as well.
Now, that's equivalent to me not only trying to guess the color of the face of the cards, but also trying to guess the color of the back of the cards. Okay, so we're now going to switch on the laser and start the experiment. So this number here gives me the number of photon pairs coming through the experiment. That's equivalent to the pairs of cards in my game. The graph here dropping down gives me the probability that I can win, that I'm guessing right.
The more photons, the more accurate it becomes. I'll stop at an uncertainty of about 1%.
And the final answer is 0.56. So if I put that into my equation, I now need to run the experiment 3 more times, corresponding to the 4 different settings of these dials.
Each run is now like a different set of rules for the quantum dealer.
And when I add them up and get the answer, if it's less than 2, then Einstein was right. If it's greater than 2, then Bohr was right. Okay, so now for the second setting.
Just remember what the experiment will show. If the numbers come out less than 2, then it's proof the dealer has been stacking the deck. This was Einstein's view.
Okay, so the number I get this time is 0.82. Now reset for run 3.
But if the result is greater than 2, then the deck cannot be stacked, and something else is at work.
Okay, so the run 3 result is minus 0.59. And finally, run 4.
This last number will finally reveal if the world follows common sense or something much more bizarre.
Okay, so our final result is in, and it's 0.56. So if we turn the laser off... Right, I better just work out the answer. And there we have it, 2.53. It's a number greater than 2. Absolute proof that Albert Einstein was wrong and Niels Bohr was right. The significance of this result is simply enormous. Just remember what it means. Einstein's version of reality cannot be true. No amount of clever jiggery-pokery with our experiment can cheat nature. The two entangled photons' properties couldn't have been set from the beginning, but are summoned into existence only when we measure them.
Something strange is linking them across space. Something we can't explain or even imagine other than by using mathematics. And weirder, photons do only become real when we observe them. In some strange sense, it really does suggest the moon doesn't exist when we're not looking. It truly defies common sense. No wonder towards the end of his life, Einstein wrote, "All these 50 years of conscious brooding have brought me no nearer to the question, what are light quanta? Every Tom, Dick, and Harry thinks he knows it, but he is mistaken." The experiment only confirms this. Whatever is happening, we just don't understand it. But it doesn't mean we should stop looking. While it's true that Einstein's dream of finding a reasonable, common-sense explanation was shattered for good, my own personal view is that this doesn't necessarily banish physical reality. Like Einstein, I still believe there might be a more palatable explanation underlying the weird results of quantum mechanics. But one thing is clear. Whether there are physical, spooky connections, whether there are parallel universes, whether we bring reality into existence by looking, whatever the truth is, the weirdness of the quantum world won't go away. It'll rear its ugly head somewhere. 120 years ago, the greatest scientific revolution ever was brought about by a light bulb. And scientists are still using powerful light sources, like X-rays, to unlock nature's mysteries. This is the Diamond Light Source. It's Britain's single largest science facility. The X-rays produced here are 10 billion times more powerful than a hospital X-ray. With that sort of power, scientists can slice into matter and glimpse those quantum secrets inside. Researchers here are using this powerful light beam to investigate new materials, which may have the potential to bring about an electronics breakthrough as great as any before. Just as the quantum pioneers of the 20s and 30s ended up bringing about a scientific and technological revolution, so this generation of physicists are set to usher in a new quantum era. An era where Einstein's hated quantum entanglement now produces unbreakable computer security, new kinds of communication systems, super-fast computers, and other advances we can't yet even imagine. And this is why quantum mechanics thrills and frustrates me. It's capricious, it's counterintuitive, it even sometimes feels just plain wrong. And yet, it still surprises us every day. And I, for one, believe that our knowledge of the quantum world is still far from complete, that there are greater truths about nature yet to be discovered. And that's still what keeps me awake at night. Welcome to a new and very strange world of nature. It's been taken over by the weird subatomic particles of quantum physics. As a physicist, I've spent my working life studying how these particles behave in the laboratory. But now I'm heading out into the natural world. I'm on a mission to prove that quantum physics can solve the greatest mysteries in biology. This is a real adventure for me. I'm very much out of my comfort zone, trying to apply the very careful ideas I'm familiar with in a physics laboratory to the messy world of living things. I believe that quantum physics could hold many of life's secrets. That deep in the cells of animals, particles glide through walls like ghosts. That when plants capture sunlight, their cells are invaded by shimmering waves that can be everywhere at the same time. And that even our human senses are tuning in to strange quantum vibrations. In the fantastic world of quantum biology, life is a game of chance, played by quantum rules.
This is what I hope to convince you of, to show you that quantum mechanics is essential in explaining many of the important processes in life, and potentially that quantum mechanics may even underpin the very existence of life itself. My quest begins with one of the most majestic sights in nature: migration. Every winter, barnacled geese arrive right on cue at the same Scottish river. The end of an epic 2,000-mile voyage from Svalbard, high above the Arctic Circle. Of course, many birds head south for winter, then back home for summer. But for decades, exactly how birds navigated with such accuracy was one of the greatest mysteries in biology. So the most recent discovery has caused a sensation. In the past few years, one species of bird has helped create a scientific revolution. I was one of many physicists who were shocked to discover that it navigates using one of the strangest tricks in the whole of science. It utilizes a quirk of quantum mechanics, one that bamboozled even the greatest of physicists, from Richard Feynman to Albert Einstein himself. So you might be surprised to discover the identity of this mysterious creature. Say hello to the quantum robin. This is the European robin. Every year, she migrates from northern Europe to the tip of Spain and back. In this laboratory in the woods, biologist Henrik Moritzen is trying to solve the mystery of how she does it. But he's found himself in my world, the strange world of quantum mechanics. Quantum mechanics describes the very weird behavior of subatomic particles. Down in this realm of the very small, we have to abandon common sense and intuition. Instead, this is a world where objects can spread out like waves. Quantum particles can be in many places at once and send each other mysterious communications.
I set out to understand how the bird finds its way, but it just turned out that the data more and more pointed towards this as the only explanation that could bring all the different results together.
Henrik's investigating a long-standing theory that robins navigate by the Earth's magnetic field. His laboratory is an ingenious magnetic birdcage. And these plastic cones, lined with scratch-sensitive paper, provide the key measurements. Henrik's artificial magnetic field is like the Earth's, except that he can point it in any direction he likes. Inside their cones, the robins always respond to the field, leaving scratches in a single direction. The big mystery is how. The Earth's magnetic field is incredibly weak, far too weak for any living creature to detect. But Henrik has found an intriguing clue by giving the quantum robin a mask.
We have a little leather hood, similar to what you put on a falcon, but just for a robin. And you have then a hole in front of one eye or a hole in front of the other eye. But what we can see is that if you cover up the right eye, you turn off the magnetic compass processing in the left part of the brain. If you cover up this eye, you turn the compass off in this part of the brain.
The robin's magnetic compass seems to be in her eyes. I can show you what's going on using my own eye. Now, we use our eyes for vision, but we also have a second light detecting mechanism. If I shine this torch into my eye, you can see that my pupil closes down. It's basically a defense mechanism to protect my eyes.
My eye is responding to particles of light, or photons.
The energy provided by the photons is clearly enough to activate chemical reactions. After all, that's what controls my eye muscles.
Light must be causing similar chemical reactions in the robin's eyes. In fact, it's the power supply for a unique form of magnetic compass inside her cells, in the weird world of subatomic particles. A place where only quantum physics can explain what's going on. To see why, imagine the chemical reactions in the robin's eye taking place in mountains and valleys of energy. To get a reaction to start, you have to push molecules to the top of a mountain. Thanks to Henrik's experiments, we now know that light does most of the hard work. But when it reaches the very peak, the molecule becomes incredibly sensitive to the slightest touch.
The key point here is that the robin's chemical compass is now balanced on an energy peak between two valleys. Going one way produces one set of chemical products, the other a different set.
Now, even a tiny change in the Earth's magnetic field can tip the molecule over the top. But the way this happens defies common sense.
The final piece of the puzzle depends on one of the truly mind-boggling ideas in physics. But don't worry if you find it hard to understand. Even Albert Einstein called it spooky.
The idea is called quantum entanglement. It involves particles that seem to communicate faster than the speed of light. In 1935, Einstein published a famous paper arguing that it was impossible. But Einstein was wrong. In recent years, extremely delicate experiments have shown that subatomic particles really are entangled. It means they can subtly and instantaneously influence each other across space. And now it seems the same thing is going on inside the robin's eye.
When a photon enters the robin's eye, it creates what's called an entangled pair of electrons. Here's how it works. Each electron has two possible states. For simplicity, I'm choosing to call them red and green. Now, here's the weird thing. Until I measure it, it's neither one nor the other, but both at the same time.
Think of the electrons like spinning disks. They're simultaneously red and green. But by firing a dart, I can force the first electron to be one or the other. So far, it's just a game of chance. I don't know what I'll get until I try it.
So I know my first electron is red. Suppose I now measure the second electron. You'd think I'd have a 50-50 chance of getting red or green. After all, that's what you'd expect in the normal, everyday world. But you'd be wrong.
In quantum entanglement, the electrons are mysteriously linked. For example, if I get red on the first, I always get red on the second. It's not a game of chance anymore. It's as if the first electron is telling the second one what to do. That's why Einstein called it spooky.
The electrons seem to know that they should both have the same color, no matter how far apart they are.
The really important part is that the two electrons needn't be the same color.
they can be entangled in a different way, so that if the first electron is red, the second one is always green. It seems that this mysterious connection is the ultimate secret of the quantum Robbins compass. Because the direction of the Earth's magnetic field can influence the outcome.
Near the equator, they may be more likely to be red-red, but near the pole, they may be more likely to be red-green. And that's the vital factor that finally tips the balance of the Robbins chemical compass.
Tiny variations in the Earth's magnetic field change the way electrons in the Robbins eye are entangled. And that's just enough to trigger her compass.
Now, finally, we can see how something as weak as the Earth's magnetic field can tip that balance one way or the other.
If the message changes, the chemical reaction tips a different way, changing the Robbins compass reading.
Suddenly it looks like it's a fundamentally quantum mechanical phenomenon in birds. It would be one of the first, if not the first, in biology.
Biologists better get used to the weirdness of physics. The robin is navigating by spooky quantum entanglement.
To see subtle quantum effects, even in a controlled, austere environment of a physics lab, is really difficult. And yet, here's the robin doing it with ease. These experiments are real and verifiable. And yet, even though I'm seeing them with my own eyes, I still find it hard to believe.
Bird navigation has brought physics and nature together as the science of quantum biology. There's a whole new world to explore. But its pioneers have found that it doesn't just affect birds. It affects every single one of us. Because the latest experiments say you're doing quantum physics right now. And believe it or not, you're doing it with your nose.
Hello, Jim. Hello. Hello, little girl. Hello. Our sense of smell is remarkable and quite different from our other senses of sight and hearing. Among the thousands of scents that we can recognize, many of them may well trigger very powerful memories and emotions. It's as though our sense of smell is wired directly to our inner consciousness. It's also different in another way. The other senses of sight and hearing rely on us detecting waves, light and sound. But our sense of smell involves detecting particles, chemical molecules. Recently, scientists have begun to realize that when it comes to our sense of smell, something very mysterious is going on.
For decades, biologists thought they knew exactly how our noses sniffed out different chemicals. But physicists like Jenny Brooks think there could be a new ingredient in the mix. And it smells like quantum mechanics.
A lot of people speak of the sense of smell and olfaction and the science of olfaction as being a problem that's been solved and we know all about it. And we do know a lot about it. We know about the ingredients, we know about the equipment that we use to smell. But I would argue that there's a little bit more to understand.
To understand more, I need someone to help me with a smell test. And Jem is going to sniff him out. Every human being gives off a cocktail of chemicals. Jem's nose could detect a single gram of it dissolved over an entire city. So she has no trouble finding the man I'm looking for. Meet Colin the gardener, a man who's used to smelling the flowers. Right then, Colin, I'm going to put your sniffing skills to the test.
Cool.
I've got a selection of chemicals here, and I want you to tell me what they remind you of.
Okay.
I'll start you off easily.
Oh, that's like a minty vapor rub.
It is, yeah.
Sort of thing, like, yeah,
this is
sort of what you'd rub,
menthol.
Menthol,
Yeah.
yep. But it's that essence.
Right, here's the next one. So you should be able to recognise this one.
That's baking with my daughter. Mm-hmm. Icing sugar, sort of thing.
Vanilla.
Vanilla, yeah.
When our noses detect a chemical, they fire a nerve signal to our brains. But different chemicals create different sensations. The standard explanation for this is to do with the shape of the molecules. The conventional theory that goes back to the 1950s says that the scent molecule has a particular shape that allows it to fit in to the receptor molecules in our nose. If it has the right shape, it's like a hand in a glove or a key in a lock. In fact, it's called the lock and key mechanism. With the wrong shape, it won't fit into the receptor. But with the right shape, it fits into the receptor, triggering that unique smell sensation. Different receptors are wired to different parts of our brains. So, when a menthol molecule locks into its specific receptor, it triggers that minty fresh sensation. But the lock and key theory has always had a problem. And Colin's next test will show you why. Okay, how about this one? Quite strong smell.
Oh, that's yeah.
What does it remind you of? What does it conjure up? What memories?
I think Christmas cake.
Yeah, marzipan.
Yeah, that's it. Yep.
Yes, almonds.
Very, yeah.
Colin identified the smell of marzipan or almonds. In fact, it's due to a scent molecule called benzaldehyde. What I didn't give him to smell was this other chemical, cyanide. Both benzaldehyde and cyanide have the same smell. They both smell of almonds. But these molecules are both very different shapes. So the lock and key mechanism as an explanation for how we smell can't be the whole story. So why would two molecules with different shapes smell the same? Quantum biology has a head-spinning explanation. It says our noses aren't smelling chemical molecules. They're listening to them. It's not just the shape of a scent molecule that matters. Let's take a closer look at this model of a cyanide molecule. The white ball here is a hydrogen atom, and the grey sticks are the bonds that hold it together with the carbon and nitrogen. But the reality isn't as simple as that. I can give you a better sense of what's going on if we look at this larger white ball. You see, atoms don't just sit still. The bonds that hold them together are like vibrating strings. And that gives us a whole new way of thinking about smell. The bizarre new quantum theory of smell is all about vibrating bonds. Chemical molecules are playing music for our noses. Imagine a receptor molecule in my nose is like my guitar. Before it can make a sound, a scent molecule has to enter my nose. And when that scent molecule is in place, its chemical bonds provide the strings, and it's ready to be played. The receptor molecules contain quantum particles, electrons. As they leap from one atom to another, they vibrate the bonds of the scent molecule, like my fingers plucking a guitar string. What's remarkable about this theory is that it tells us our sense of smell is about the vibrations of molecules or wave-like behavior, and not so much about the shape of a particular scent molecule. Our sense of smell may be much more like our sense of hearing. A particular molecule, say that of grass, will vibrate at a particular frequency. But a different molecule, say that of mint, will vibrate at a different frequency.
This would explain why cyanide smells like almonds. The two molecules have different shapes, but their chemical bonds just happen to vibrate at the same frequency.
The quantum vibration in the odoron is almost literally like a particle of sound. So yeah, we're saying that the process of smell could be exactly like an acoustic resonance event. It could be very analogous to hearing and seeing, actually.
But can we really be listening with our noses? A bizarre theory needs a bizarre experiment to test it. Here's how it works. Scientists used a molecule that smells fruity, like orange blossom. But if the theory is right, then I should be able to change its smell by changing its vibrations.
The molecule contains lots of hydrogen atoms like this, bonded to carbon atoms. But what if I were to replace all these atoms with a different form of hydrogen called deuterium? Now, it won't change the shape of the molecule, but it will change the way it vibrates. And here's why. Deuterium is twice as heavy as normal hydrogen, and so it vibrates more slowly. Now, different vibrations mean different smells. So if I were to make a new form of this chemical, all packed with deuterium atoms instead of normal hydrogen, it should smell different.
Quantum biologists found a unique way to carry out this experiment. A smell comparison using the real experts in fruity aromas. Fruit flies. First, the flies were trained to avoid the modified version of the fruity molecule.
To be honest, I haven't got a clue how you go about training a fruit fly, but apparently you can.
In the laboratory, the flies had to pass through a kind of maze. They were then given a choice. Go right for the nice fruity smell, or left for the nasty modified version. They could definitely smell the difference. They always preferred the original and turned right. The fruit fly experiment gives hard evidence that quantum smell theory really works. But ultimately, it works in harmony with the lock and key theory. First, the scent molecule fits into the receptor. Then those molecular vibrations take over. Incredible as it seems, flies, humans and dogs may be smelling the sound of quantum biology.
Our sense of smell is fascinating and mysterious as it is. But to think that when I encounter a particular scent and that sets off a whole wave of memories and emotions in my mind, that it's underpinned, that it's triggered by quantum mechanics, I think makes it even more remarkable. The mysterious influence of quantum physics reaches into every corner of the natural world. In fact, it inhabits the walls of every living cell on Earth. Because the latest experiments suggest a magical solution to one of the greatest mysteries of nature. The miracle of metamorphosis. The transformation of a tadpole into a frog has never been fully explained. In little more than 6 weeks, the tadpole breaks down, then reassembles in its adult form. But the big mystery is how it happens so fast. When you think about it, there's nothing more extraordinary than a tadpole turning into a frog. Take its tail, for example. Over a period of several weeks, it gets reabsorbed into the body, and the proteins and fibers that make up the flesh get recycled to form the frog's new limbs. But for this to happen, trillions and trillions of chemical reactions work together, breaking molecules, forming new ones in a carefully orchestrated dance. But the fibers that hold flesh together are very, very strong. They're a bit like these ropes holding my raft together. In order to dismantle the raft, I'd have to undo these very tight knots. You can think of it like this. A tadpole is held together by long ropes of proteins, knotted together by chemical bonds. The bonds are so strong that they should last for years, much longer than the tadpole's entire lifespan. So how can it turn into a frog in just a few weeks? The explanation involves one of the most important molecules of life. Tiny widgets in all our cells called enzymes.
The enzymes are the actual machinery of the cell. They're actually the little machines inside cells that do the chemical transformations that are involved in everyday life. They're absolutely crucial. And the reason they're so crucial is because what they're able to do is to accelerate chemical reactions by enormous amounts.
Let me show you just how quickly enzymes get to work. Inside this bottle is a substance called hydrogen peroxide. You're probably most familiar with it as the chemical used to bleach hair. In fact, I obtained this sample from my local hairdressers. Hydrogen peroxide is also produced in the body, and it's the job of the liver to get rid of it. Now, the way it does that is using an enzyme which breaks down hydrogen peroxide into water and oxygen. Now, to show you just how quickly this enzyme works, I'm going to do a quick demonstration. I've got some liver here which I've chopped up in order to release the enzyme. Now, watch what happens when I add this liver mixture containing the enzyme to the hydrogen peroxide. Watch how quickly the oxygen is released. Just 100 grams of liver fired my rocket nearly 20 feet. Liver enzymes make the breakdown of hydrogen peroxide incredibly efficient. It happens 1 trillion times faster. That's 1 million times faster than it would otherwise. In metamorphosis, it's enzymes that dismantle the tadpole's tail. And that means breaking down an incredibly tough protein called collagen.
So collagen is one of the most important proteins of the biological world. It's the protein which actually gives that resilience, that elasticity to tendons, to cartilage, and of course to our skin as well. And in the tail of the tadpole, it provides the kind of scaffold, right, that supports that structure. Now, when the tadpole is transformed into the frog, what you need to do is to essentially have an enzyme collagenase, which will literally snip the collagen down into small pieces and thereby take that scaffold apart.
But how do enzymes break chemical bonds apart so incredibly fast? Let me show you why it's a problem only quantum biology can solve.
Think of it this way. All these different parts of the knot are like subatomic particles, electrons, protons, that hold the different parts of the molecule together. Now, to untie the knot, enzymes have to move protons about. But as you can see, this takes quite a bit of effort and a lot of time if there are many, many knots to unpick. Physicists have a fancy way of saying, put in effort to get something done. They say you have to overcome an energy barrier.
Okay, here's my energy barrier. And here's my proton. To break a bond apart, it needs enough energy to get over the barrier. The trouble is, when we work out how long this would take, it's much too slow to break down a tadpole's tail. But this is where protons turn into ghosts.
I wouldn't blame you for thinking that this is an idea that a clever theoretician has come up with, that it's just mere speculation, something that we have no proof of. But we do. It takes place all the time.
In the quantum world, protons don't have to go over barriers. They can tunnel straight through.
Tunneling strikes at the very heart of what is most strange about quantum mechanics. It's like nothing we see in our everyday world. A quantum particle can tunnel from one place to another, even if it has to pass through an impenetrable barrier. They're not solid objects like balls in our everyday world. They have spread out, fuzzy, wave-like behavior that allows them to leak through an energy barrier. A particle can disappear on one side of the barrier and instantaneously reappear on the other.
In nuclear physics, this effect is a proven fact. Without quantum tunneling, the sun simply wouldn't shine. But I never thought I'd see it in a tadpole.
It's hard to stress just how weird this process is. It's as though I would approach a solid brick wall and, like a phantom, disappear from one side and reappear on the other.
The most important advantage of tunneling is its speed. It happens incredibly quickly, much faster than if protons go over the barrier.
As a nuclear physicist, quantum tunneling is my bread and butter. Subatomic particles like protons do it all the time. But what has this got to do with biology?
The answer is that without quantum ghosts, the metamorphosis of a tadpole would be impossible. Remember, chemical bonds are basically knots. Tunneling unties them fast.
Have a look at these two knots. Now, on the face of it, they look identical, but there's a subtle difference. This knot has the two short ends of the rope on the same side, whereas this one has the two short ends on opposite sides. Now, you think that wouldn't make a difference, but it does. You see, this knot is very hard to break, whereas this one is easy.
Quantum tunneling turns strong knots into weak ones. So, in a tadpole, the entire collagen scaffold breaks apart easily. And finally, other enzymes rebuild it in the shape of a frog.
The quantum tunneling of particles is one of those weird features of the subatomic world that a physicist like me is very familiar with. After all, it's responsible for radioactive decay, and it goes on inside the sun. It's the reason why the sun and all stars shine. But to discover that it's going on inside every cell of every living organism on the planet, because every cell contains enzymes, now that I find truly amazing. Quantum biology casts its spell over every living creature. We've seen that birds, mammals, insects, and amphibians are governed by the strangest laws in science. But the most dramatic recent breakthrough concerns the single vital process on which all these forms of life depend: the conversion of air and sunlight into plants. This fine specimen is a Larix decidua, or European larch. It's about 100 feet high, and right at this moment, passing just this side of the planet Venus, is a bullet with this tree's name on it. The bullet is a photon, nearing the end of its long journey from the sun. Its ultimate destiny is to kick-start a series of chemical reactions that underpins all life on Earth. Photosynthesis. Every second of every day, 16,000 tons of new plant life are created on Earth. And for me, it's incredible to think that our existence on this planet depends on what happens in the next trillionth of a second. The crucial first stage of photosynthesis is the capture of energy from the sun. It's nearly 100% efficient, vastly superior to any human technology. But the way that every plant on Earth achieves this is one of the great puzzles in biology. When it turned out that quantum weirdness might hold the answer, physicists could hardly believe it.
It was like a revelation. It was very exciting because I was used to work on problems that were quite abstract. Experiments, I'm a theoretician, but I always related my theory to experiments that were very clean in the lab, things that you can control. But now finding out that the things that I knew can help me to understand better how nature works, really, I don't know, scientifically, it was like a new inspiration to my life as a scientist. So I really, as I would say, I fell in love with this field.
Textbook biology says the color of green plants comes from chlorophyll molecules. Inside the living cells, they absorb light from the sun. This energy is then transferred incredibly quickly to the food-making factory at the heart of the cell. The entire event takes just 1/millionth of a second. When the photon hits the cell, it knocks an electron out of the middle of a chlorophyll molecule. This creates a tiny packet of energy called an exciton. The exciton then bounces its way through a forest of chlorophyll molecules until it reaches what's called the reaction center. Now that's where its energy is used to drive chemical processes that create the all-important biomolecules of life. The problem is, the exciton needs to find its way to the reaction center in the first place. Textbook biology can't explain how the exciton does this. Because, of course, it doesn't know where it's going. It just bounces around like a pinball in a process called a random walk. Sooner or later, it'll pass through every single part of the cell. But this isn't the most efficient way to get around. Because when the exciton eventually does reach the reaction center,
it's by pure chance. If the exciton just blindly and randomly hops between the chlorophyll molecules, it would take too long to reach the reaction center and would have lost its energy as waste heat. But it doesn't. Something very different must be going on. The vital clue comes from recent experiments that stunned the world of science. Chemists fired lasers at plant cells to simulate the capture of light from the sun. They confirmed the exciton wasn't bouncing along a haphazard route through the cell.
This original understanding didn't explain what we were observing in the lab. So the mystery relies in, okay, so then what is the explanation for what we are observing in the lab?
The solution is that plants obey the most famous law in all of quantum mechanics: the uncertainty principle. It says you can never be certain that the exciton is in one specific place. Instead, it behaves like a quantum wave, smearing itself out across the cell. The exciton doesn't simply move from A to B. In a bizarre but very real sense, it's heading in every direction at the same time. It's spreading itself out as a wave so that it can explore all possible routes simultaneously. This strikes at the very heart of what's so strange about quantum mechanics. The exciton wave isn't just going this way or that way. It's following all paths at the same time. That's what gives it such incredible efficiency. The beauty of it is, if the exciton is trying every route to the reaction center at once, it's bound to find the fastest possible way to deliver its energy. It's hard to express how incredible this discovery seems to physicists like me. Biological cells are full of the random jiggling of billions of atoms and molecules. But somehow, excitons maintain their form as beautiful, perfect quantum waves, transporting the energy that guarantees life on Earth.
It opened a whole new scientific path for me. And I really enjoy the fact that to be able to understand fully what is happening there or in the plants, you have to interact with scientists that have completely different approaches, like biologists and chemists. But we all have to come together to actually understand what is the relevance of this. So for me, this is one of the most exciting parts of this field.
Real scientific experiments leave no doubt. The strange hand of quantum mechanics has shaped the entire living world.
It's not a surprise that you should find quantum tricks being used in biological systems. The reason is because they're better.
Quantum entanglement is normally seen in the tightly controlled conditions of the physics lab. But now we know that robins use it to navigate with extraordinary precision. Quantum vibrations mean our noses listen to chemicals, enhancing our perception of the world around us. The living cells of all animals depend on protons that vanish and reappear like ghosts, speeding up the vital processes of life. And photosynthesis reveals the big picture. A shimmering world where quantum waves capture the sun's energy in an instant.
Sometimes people say, but physicists have been looking for this for decades. Well, biology has had millions of years.
The ultra-modern science of quantum mechanics is an ancient fact of life. For the end of my journey, I want to take these ideas to their logical conclusion. Of course, as a scientist, any speculations I have to be backed up by careful experiments. So I want to concoct a thought experiment that helps me to answer the biggest biological question I can think of. Does quantum physics play any role in the mechanism of evolution itself? In 1859, Charles Darwin stunned the world with his theory of evolution by natural selection. He went on to explain the differences between humans and other apes. 150 years later, there's no doubt that Darwin's theory accounts for every living organism on land and sea. But I'd like to explore the latest extraordinary interpretation of his ideas. Could there be a quantum theory of evolution? Can quantum evolution explain how the snail got its shell? The snails I'm used to seeing in my back garden tend to have rather bland, boring shells. So have a look at this beauty. The patterns on its shell very perfectly match the lines on the stem. It's called a banded snail, Sepia nemoralis. And the pattern isn't there by accident. Come and have a look at this. Less well-adapted snails are more likely to be found here. This stone is called a thrush's anvil. The song thrush is the snail's main predator. It catches the snail and smashes its shell against the stone to get to the snail. Now, what I can see here is that there aren't many banded snail shells, suggesting that its colours camouflage it very well, hiding it from the bird. Darwin's theory says that evolution depends on variation within a species. Snails with camouflage are more likely to survive and reproduce, passing on their shells to the next generation, so that the species as a whole becomes better adapted. So variation, the random differences between snails, is the driving force behind their evolution. Now, all species evolve and adapt to their environment. But the question I'd like to explore is whether quantum mechanics plays a role in this. The only way to find out is by scientific experiments. So my adventures in quantum biology finally bring me home, to the University of Surrey. Here in the laboratories, I'm planning a new analysis of the most celebrated molecule in science, deoxyribonucleic acid, or DNA. Its double helix holds the genetic code for every living organism. It's a remarkable fact that Darwin himself had no idea what created variation in the species. The structure of DNA wasn't discovered until 1953 by Francis Crick and James Watson. The most famous feature of DNA is, of course, its beautiful double helix structure. But that's just scaffolding. The real genetic secret lies in between. The 4 different coloured molecules are called bases. The color code on one side, say blue, red, blue, forms a gene that parents pass on to their offspring. A gene is a bit like a jigsaw puzzle. It fits together like this. A full strand of the double helix forms a colored pattern. But the other strand always pairs up the same way. A blue base always goes with yellow, and green always goes with red. Because only those colors have the right shape to fit together. What Crick and Watson realized was that this provides a mechanism for passing on the genetic code. When cells reproduce, the two strands of DNA separate, ready to be copied. But red still goes with green, and yellow still goes with blue. So, bit by bit, the cell creates two new strands. Two perfect copies of the entire genetic code. So far, there's no genetic variation. This new copy is identical to the original. But here's the interesting bit. During the copying process, something very important can happen. Sometimes mistakes creep in. They're called mutations. Let's have a look at these two bases here. The two prongs that hold them together are subatomic particles. They're protons. They're basically the bonds between the strands of DNA. These protons can jump across to the other side. If the strands split when the protons have jumped across, they find themselves in the wrong position. Now, this red base will no longer bind to a green base. Instead, it has to bond to a yellow base. Slotting this back in, we see that now this copy is no longer identical to the original because I have a yellow base here instead of a green one. We've brought in a genetic mutation. Jumping protons would change the snail's DNA. It could make a new gene for camouflage shells. The question is, how do protons jump? It's my belief that quantum spookiness can take over. Now, for these mutations to take place, the protons have to overcome an energy barrier. And if you remember what happened with enzymes, well, you can probably guess what's coming next. Protons can behave as if barriers don't exist. They tunnel straight through. But does this ghostly effect really happen? My colleagues in biology are already looking for the very first evidence of quantum mutations.
Biologists didn't really even know about quantum mechanics, so when you tell them that, particles can be in two places at once, they kind of say, well, not in my cells, they can't.
Our experiment involves samples of bacteria. The first sample is prepared in normal water, containing hydrogen nuclei, or protons. When the bacteria reproduce, we simply count the mutations. But if our theory is correct, then we should be able to change the rate at which mutations occur. Remember how we tested the quantum theory of smell? What if I replace the proton with its big brother, the deuteron? This is the nucleus of an atom of deuterium. Now, crucially, a deuteron is twice as heavy as a proton, and this should influence how easy it is for the deuteron to quantum tunnel. Quantum mechanics is full of surprises. Protons tunnel easily. Deuterons don't. These heavier particles are much more likely to bounce straight back. So the second sample of bacteria is prepared in heavy water, which is full of deuterons.
Our theory says you should get far fewer mutations. And so far, the results are extremely encouraging.
The preliminary experiments that we've done gives us a hint that the mutation rate is indeed depressed in deuterated water. We find that it is lower. So my hunch is that we're right, but we'll have to wait a little while before we're sure.
Final proof lies in the future. Even if we're right, quantum tunneling is a rare form of mutation. But our results promise hard evidence for a new explanation of one of the most fundamental processes of life.
Even the merest possibility of a new quantum mechanism for evolution itself is tremendously exciting. In fact, the story of quantum biology is only just beginning. What the frog, the robin, the fruit fly, and the tree have shown us is that real quantum effects are going on in nature all the time. And if there's anything we've learned from the history of quantum mechanics, it's this: we can never be certain where new discoveries will take us next.
Quantum biology is a revolution in science. But it's time I got back to the physics department.